Okay, a bit more work on collisions. So giving us a table here to fill in for elastic collisions and inelastic collisions, and we have to tick off the things which are true for that type of collision. So total momentum for the objects is conserved. Right, we can always use conservation momentum in collision, so that doesn't matter whether we've got elastic or inelastic. The momentum isn't going anywhere else. Momentum exists in objects, and if we've only got two objects hitting each other, then the momentum must stay in those and be conserved through the collision. Total kinetic energy of the objects is conserved. Well, it is in elastic collisions, but that's the whole point of inelastic ones, that some of the kinetic energy of the objects before the collision is then transferred off into things like heat and sound or whatever it may be, deformation of materials. So we can't have that. We can't do conservation of energy, or at least conservation of kinetic energy, through the inelastic collision. But total energy is always conserved. That's one of our fundamental properties of physics. So yeah, in that case, we've got two more ticks there. It's just in an inelastic collision. How do we go about calculating this? As soon as you start throwing in losses, which is really what we're getting on an inelastic collision, then we've got big problems. So we can't use that so much as an analysis tool, but energy, total energy is conserved. It's the kinetic energy bit, the bit that's easy to calculate, that isn't conserved through the inelastic collision. And then the magnitude of the impulse on each object is the same. Well, yeah, again, because that's just dealing with momentum. Impulse and momentum, impulse is the change in momentum of an object. And from Newton's third law, this came up in one of the earlier videos, that equal and opposite force exerted by these two objects hitting each other, that equal and opposite propagates it through itself through the idea of impulse. So we get equal and opposite impulses acting. That's why they've said magnitude here. So the magnitude is the same, is the direction that changes. So we got 7 ticks here. It's just this one for kinetic energy on the inelastic collision. So that's the only one really you need to keep in mind. Right, so in part B, we're on to snooker ball on a smooth horizontal table. Physicists love snooker questions. Hit by a snooker cue. Here's the simplified graph of force against time. All right, so we've got force here, notably in kilonewtons. We've got time in milliseconds. So these might end up cancelling out as we're multiplying them together. We've got a 10 to the 3 and a 10 to the minus 3. But let's see what they're after. Describe how the velocity of the ball varies between t is 0.6 and 0.9 milliseconds. Right, these lines are making my eyes go funny, but I think that's the flat bit. We measure, so that's from here to here, which does look like 5, 6, 7, 8, 9. Yeah, so that is the flat bit. So in this portion of the graph, we've got a constant force, constant F, equal to, oh my word, again, the line's 2.2, I think that is 2.2 kilonewtons. So if we've got a constant force, we've got a constant acceleration. So we've got a constant rate of change of velocity. So we've got well, let's say an increase in velocity, at a constant rate, because the force is constant. So increase in velocity at a constant rate. Okay. Use figure 1.2 to calculate the impulse acting on the ball. So remember, our impulse is the integral of f dt. It's the area underneath the graph. Handily, they've made these triangular bits symmetrical, because we got 0.6 going up and we got 0.6 coming back down. So we can just turn this into one single rectangle of 0.9 times 2.2. And yes, these are going to cancel. The milliseconds in the time and the kilonewtons in the force are going to cancel out. So that's 0.9 times 10 to the minus 3 multiplied by 2.2 times 10 to the 3. So they're just going to disappear. And we're just left with that 0.9 times 2.2, which is 1.98 Newton seconds. So yeah, that's straightforward as an impulse. The mass of the snooker ball is 140 grams. Calculate the final speed of the snooker ball as it leaves the cue. Well, that impulse is the change in momentum. It's told us that it started at rest. That's in the question. So that is the final momentum that we've got of the ball. So that 1.98 is going to be equal to the mass. They've given it in grams. So let's flip it over to kilograms times the final velocity. So we've got to divide through. So V is going to be 1.98 divided by 0.14. So that's going to be, well, it's going to be a little over 14 because 14 squared is 196. So it's going to be, say, 14.1. And what sort of accuracy have they given us here? Not very much here. But I don't know. Yeah, I mean, we're going to struggle, I think, to say 14.1. We've got 2 sig figs on all the others. So let's say that is 14 meters per second to 2 sig figs, because that's what we've got all over the place on the others. Yeah, so yeah, it's quite a nice one. It brings in, again, it's refreshing our memory on all of this description and terminology around our different types of collision, and then a little bit of graph work. But yeah, hopefully this is showing that collisions aren't really that scary once you've got the idea what an impulse is in your head and you're dealing with this thing, and the calculus isn't worrying you too much, then yeah, impulse is fine.